Hey guys, it is Tuesday and you have made it to the Techno Lair to hang out with me, the Oscope Wizard. I'm Gabe, the Oscope Wizard, and hopefully you're here to nerd out for a little while. I don't know what you did this weekend, but here it was quite warm, so we sought respite in pools and bodies of water everywhere. I have the hot tub now converted to a cold tub that is inflatable and sitting on my back deck, so I spent some time in there to just try to chill out, literally to chill the body temperature out of my body. It was so hot. It was so hot. Hopefully you guys had a wonderful weekend. And also this weekend, I spent quite a bit of time. Let's see if I can get it working. Hopefully everything is working. We will shortly find out. But quite a bit of time messing with my project, our quest, the DIY Sonos style amplifier built around a Raspberry Pi. You can see this is a video of me soldering things, desoldering things, generally just trying to reorganize the box to make a lot of sense, because if you will remember, I have been battling angry cicadas, the noise of electrical bugs crawling through my circuitry, making it from somewhere to my speakers. And as it turns out, after much digging and much pontificating and thinking and experimenting and actually measuring, I hooked my oscilloscope up to make some measurements. It turns out that most of the noise is coming from the Raspberry Pi Zero itself. It is quite a noisy little board. Actually, I've mentioned it before that it has a super noisy power supply, so when you try to power things with it, it creates all kinds of chaos. And normally that wouldn't be a big deal, because a lot of times people are hooking up screens, so you can't really see the noise because the screen doesn't show it. But when you hook up something that makes audio noise, you can definitely hear it. So if I hooked up my little DAC, my digital to analog converter chip, to the Raspberry Pi to power it, it would create all kinds of hiss. So what I ended up doing, as you can see on this video, is moving my DAC from near the Raspberry Pi. Here's the actual board now. So I moved it from near here, which is the Raspberry Pi, to way over here. And the only thing hooked up to this power board right here, this DC to DC converter, is my digital to analog converter. So in an effort to try to isolate it from the Raspberry Pi, this guy over here. So that took quite a bit of time, quite a bit of doing, quite a bit of experimenting, but I figured it out. Thank goodness. Thank goodness. So one of the things that I learned was EMI is real. EMI being electromagnetic interference. EMI is definitely real, and it was rearing its ugly head in my design by getting into that board over and over again. The last time we joined together to nerd out for a little while, I worked on using this button, this volume knob, to switch between the internal and external inputs of my amplifier, and I wanted to have an external input in case I wanted to hook up an iPhone or a tablet or a computer, or who knows, a turntable, a guitar, a car audio system, I don't know, crazy things. But I wanted to be able to switch from the Raspberry Pi's audio system to something external, and so this button is allowing me to actually do that, and you can hear the pop, or maybe you can't hear the pop, but every time I switch, it pops the speakers on and off, because what I wanted to make sure happened is when I was on the external input, the amplifier was always on. And you guys got to see me flounder around and write some terrible, terrible Python code that ultimately did work, but wow, it was embarrassingly bad. So I found out that the GPIO of the Raspberry Pi actually supports hardware interrupts. And what does that even mean? Let's see if I can figure out how to show this. I think I need to. Let's show it if I can. I go over here to the desktop. Let's log in. I just want to show you what I mean. So I need to log into my Pi. And I have not changed the default password or the default name, mood.local and mood audio. Now, I wrote some code. It was called sudo. It was called relay toggle.py. That's what we were running. This is in our magical service that we start. So the big thing is this routine right here. This is my callback. And what you can do is in your Python code, you can add an event to your GPIO. So on my GPIO, I added an event detect that detected when my button pin, so that is the volume knob button, has a rising edge. So when it turns on. And every time the GPIO detects a rising edge, it sends a callback to this subroutine. Hold on, as I try to master the English language in front of you using my perfect recall. So every time it detects a rising edge, the program has a hardware interrupt, which is really cool. Hardware interrupts are awesome because they stop whatever is happening in the program, which right now all is happening is while true, just sleep. When a rising edge happens, it's like, all right, pause what you're doing, go and run this code right here. In college, I used to do this a lot with microcontrollers. That was a pretty big deal to learn how to use hardware interrupts on a microcontroller. And in real life, hardware interrupts are still cool because when people press buttons, they want things to happen now. It is so annoying when you go to a gas station pump and they aren't using hardware interrupts and you're trying to type in your zip code and it is taking forever. When I press in a button, I want it to have instantaneous feedback. That is what this provides. So every time my button is pressed, it goes to this subroutine called external input _ callback. And you can do other things with the hardware interrupt, which is kind of cool. But what I do is I switch my pin. So the switch pin is the thing that is controlling the amplifier. Every time the button is pressed, I just invert the pin. So if it's a 1, I send it to a 0. If it's a 0, I send it back to a 1. And then I check to see, what do I check to see? If the external input is active, then I want to always have the amplifier on. So I don't want it to ever go to sleep. So if the external amplifier or the external input is not on, I would like you to remain in your sleep state if you can. So anyway, hardware interrupts, really cool, and it makes for better code because this creates a second thread. I don't know if you wanted to get into multi-threading, but it allows the processor to do a few things at the same, or at least presumably at the same time. To a human, looks like the same time, because we don't operate at machine speed. But today what I would like to do, if I can turn on my agenda, this is the agenda from last time, but what I would like to do is make blinking lights happen, and maybe even show the volume. Maybe. We'll see. I know that I want to make blinking lights happen, and maybe we can get to the point where the lights can represent the volume, but what I got here is very exciting. I got this, if I can, let's get the camera to focus on it. Focus on this, please. There we go. This little thing right here is a ring of LEDs. It is a Ws2812 B LED ring. If you Google Ws2812 B, you will find all sorts of different LED configurations, but these are the Ws2812 LEDs inside of this module, it's actually a module, and inside of the module are 3 LEDs. In the case of mine, it is RGB, so red, green, and blue LEDs. And you can control them with some digital logic. So guess what I have? I have a whole bunch of digital logic on my Raspberry Pi, and I'm going to attempt to control this LED to make it do things. I would like it to light up at the very least, and as I turn the volume, I want the lights to illuminate to indicate how high the volume level is. So I want it to like get more LEDs lit as the volume gets higher, and fewer LEDs are going to be illuminated as the volume gets lower. I also thought I could do other cool things like change the color of the LED based on the input that I'm using. So maybe Bluetooth is blue, maybe Spotify is green because Spotify's colors seem to be green. Maybe AirPlay is, I don't know what color AirPlay is, maybe gray? I don't know. Maybe red for Apple? Red. I could just, a red ring of LEDs does not bring a lot of great memories to my mind. If anybody ever had an Xbox original, or no, the Xbox 360, it would get that infamous red ring of death, and that was always bad. So I don't have a lot of fond memories of red rings of LEDs. So maybe not a red ring of LEDs, but I would like to know how to hook it up. So I have a couple of little wires over here on the side. So my black wire is ground, my red wire is voltage, and my blue wire is connected to my Raspberry Pi. Let's see, on GPIO, if I turn my camera so you can follow me a little bit, it's on GPIO 12. And as it turns out, when I did a little bit of research into the Ws2812. Let's check this out. The Ws2812, the data sheet. Of course, we got to go to a data sheet because we need to understand how things work. At least we want to try. But the Ws2812 is an intelligent control LED integrated light source. So it has both digital logic inside of this little module plus the LEDs. And it is very tiny, so it has a couple of solder pins. Those are all soldered down on this ring, on this PCB for me. But it has VDD, ground, and then a data input and a data output. And the way it operates is you daisy chain these LED modules together. So there's a bunch of LED modules on this little board, and they're all daisy chained together, data in to data out. And then you could daisy chain multiple boards together to make really cool, people make all kinds of cool light displays with these little guys. But it looks like it uses a single data lane, so data in. It is just a single data lane, and it uses 24-bit bursts using a single NRZ communication mode. So that's NRZ, not return to zero, or non-zero return. I think non-zero return. But it's got a kind of an interesting protocol that uses pulse widths. So in the data sheet, it talks about the data transfer time. And zeros and ones are encoded using different pulse widths. So a 1, while the voltage is low, is encoded with a short pulse width. And a 0, while the voltage is low, is encoded with a long pulse width. And I was just curious, like, what does that look like? Well, good morning. Thanks for joining, guys. I appreciate it in the chat. And if I make a mistake in the chat, please let me know. I do have it open, and I can see it, so please let me know. Great to see you, Joe. So the pulse width modulation is essentially what we're using to send these data bits to this LED ring. But I wasn't sure exactly what that looked like, so I thought we could take a look at it with the oscilloscope to see what it does look like. First things first, we need to hook all this up. So let's see if we can follow along, if I can adjust my camera so we can see. So ground. first, let me get my scope plugged in. So I have a scope probe right here with a couple of little clips on the end, just to facilitate easy grabbing of my pins. So I'm going to clip ground to ground, and then I want to clip the business end of my probe to data input. And this is going to allow me to see, hopefully, it will allow me to see the data flowing into this LED. Now, the next thing I need to do is connect ground, and then connect power, which is this pin right here. And then I'm going to connect my data pin. Pull off this little putty. I had my pin puttied over, or my lead puttied over here just so I wouldn't lose it in my rat's nest of wires. I think I might wire wrap this when I get everything set up. I don't know if you guys have ever wire wrapped, but I did a lot of wire wrapping in college. And I have a wire wrap tool. I got some wire wrap. I don't know why I couldn't wire wrap. So I was thinking about wire wrapping. Okay, so here's my LED light. I might even be able to center the camera on it so you can see it a little bit better. I think that's the connection. I need to write some code to make all of this work. Now, I go back here. So the datasheet's cool for telling me the physical layer communications. But to make all of these ones and zeros happen, I have to write some Python code, I think. Luckily for me, when I Googled Ws2812 B LED Raspberry Pi, it turns out this thing is called a NeoPixel. And thankfully, one of the beautiful things about the Raspberry Pi is it has a huge following and a bunch of people, a bunch of hobbyists writing code for it all the time to make it do neat things. And people have written a Python library to control these NeoPixels, and it's called the Neopixel Library. And if you go to Adafruit, learn.adafruit.com, you can get the instructions on how to set it all up. So essentially you install the library using pip, and they are very clear. Use Python 3. Luckily, our mood audio defaults to Python 3. So I installed Adafruit Blinka, I think it's called the Circuit Python library, and then, here's Circuit Python, and then you have to have Adafruit Blinka, and then you have to have the NeoPixel library. So all of these are installed with these two commands. And then once you have that installed, you can do things like make a little program. So I thought we could make a little program. Let's go to my terminal. Let's Control X out of this. Sudo nano, let's call it LED test.py. We will just make something up. Let's drag this out so I can see what I'm doing a little bit. So I need to import board. I need to import Neo. So board is the Circuit Python library. NeoPixel is the NeoPixel library. And then I need to define an object that is going to be my pixels. So pixels equals NeoPixel dot NeoPixel. I don't know why the libraries have like NeoPixel dot NeoPixel. Board dot. Now this is where I tell it what pin I have my NeoPixels connected to. I have it connected to pin D12, and my pixel ring is 12 LEDs, and so that is how you would define that. So I have it connected to my pin and the number of LEDs in my NeoPixel setup. Now, the next thing that I can do is tell it to turn on a pixel. So my pixels are RGB, which is pretty cool the way these pixels are addressed. So if I just copy that code, and I'm just going to paste it in here into my nano over here. Nano window, Control V, there we go. So this is telling the program to write to pixel 0, so the first pixel, 0 to 11, and I need to write 255 to the R, and then 0 to the RGB, green, and then 0 to the blue. So it should light up the red LED to maximum brightness. That's what this program should do. Let's save it and see if it does do that. And then it probably won't, and then I'll be like, I don't know what's happening. Why do programs do this to me? So one of the things that you have to do is run all of these as sudo. So you can see right here, there's a big note. For NeoPixels to work on the Raspberry Pi, you must run the code as root, which means sudo. I don't know why you have to do that. That's a little weird, and I'm not sure what that's going to do for running this as a service. I didn't have to run root to do my rotary encoder or do my button, but for some reason to use CircuitPython, you have to be root. So okay, so I called it LED test. So let's do LED test.py, and I am going to run that. But before I run that, let's show let's move this over here so you can see what happens. Okay, so now everybody should be able to see the board and the code running at the same time. When I run the code, does anything happen? Yes! I got a lot of lights, so you can't really tell. But you can see one of the LEDs is illuminated. Look, LED, this red LED. Let me turn off more lights. How do I turn off this light? Does that show? Yeah, you can see the LED is on. For reals, for reals. One of the neat things that happens is it bursts data, and then it holds the data in the circuit for you, so you don't have to constantly rewrite it over and over again. So let's see if we can see all of that happen on the oscilloscope. Let's turn the oscilloscope on. So here's the oscilloscope looking at that data line. I am going to reissue that command, and we will see if we can detect it. So I need to make this a normal trigger. So only trigger when you see data. Now, this should be a 3.3 volt signal. So I have plenty of range over here. I'm going to issue that command again. So you can see, boom. There's the string of ones and zeros going out to my LED that's actually controlling it. Let's adjust my program so that it blinks the LED. I think I can do that. Let's go back to my desktop. Let's adjust it a little bit, because I promised we were going to blink LEDs, and I would hate to back down on a promise. So sudo nano. Coding is so exciting to watch. One of the wonderful things about coding is that everybody is better at it than you are. When you're coding in front of somebody, people will always, so I need to import time because I want to sleep for a second, will always criticize the way you're coding. It is just human nature. They can't help it. So while true, let's make an infinite loop. Infinite loops are always a good choice in a program. What you want is an infinite loop that never ends. And then I want to sleep this program for, let's just sleep it for half a second. Let's sleep it for a second. And then we'll write to that same pixel, pixels 0. Let's make it all zeros. So we'll zero out everything. And let's do time.sleep 1 again. So we'll turn it on, we'll wait a second. We'll turn it off, we'll wait a second. We'll turn it on, we'll wait a second. Presumably that's how this program will work, and it will just go on and on forever ad infinitum. All right, we'll run it. Let's see, you can see the LED over here. I'm pointing at it. Let's see. Oh, let's see, what did I do wrong? I have something incorrect. Of course I do. True is not defined. That's interesting. Because because I say because because there was a YouTube video one time. There is still a YouTube video. You can look it up. It is called ... And it is just one of the most hilarious YouTube videos that I've ever seen. It's just a game review. What is it? It is a game review by Axman13. ... And the narrator reads the review as written with spelling mistakes and typos and everything, and it is just spectacular. And one of the things the poor Axman13 does is misspell because because. So that is a truly inside joke, inside to my head. You are welcome. Thank you for joining me in my head. But Python is super tricky about cases and spaces. So while true, true being capital T. So now it knows I wanted that to be true all the time. Now let's try to run it. Okay. Is it blinking? It's blinking! It's blinking, guys! We made a blinking LED! Yay! It always feels good. It always feels good when it works. It always feels good when it works. Oh my goodness. Let's turn back on my oscilloscope to see what that's looking like. So you can see I'm issuing commands. I need a little bit more time because if you remember the data sheet, which I don't know how you would remember the data sheet. I can barely remember the data sheet. The times hour are, let's get this out of the way for a second. 0.4 microseconds, 0.8 microseconds, and then 0.85 and 0.45. So slight different timings, but let's see if we can find times in our oscilloscope that actually correspond to these things. What that all is telling me is the data transfer time needs to be 1.25 microseconds for a total bit. Is that what that's saying? Or for 2 bits maybe? Okay, so let's zoom out a little bit because I'm at 40 nanoseconds of division and I need to be at microseconds. So let's grab some microseconds. That might be too aggressive. Here we go. Here we go. Whoops. Whoops. Let's scooch that over a little bit. Still prefer my knobs and buttons. All right, so there is the whole transfer. Let's do a single and just examine it a little bit. So I'm looking at an entire transfer. This is a transfer to turn the light, I don't know, on or off, one or the other. Let's zoom in, check it out. Okay, do these things actually correspond to the times that are allegedly happening? We can probably figure out if this is a 1 or a 0. All the times are the same. This kind of makes me feel like it's a 0. I don't know. Let's make some measurements. So measure. I have a measurement called pulse. So what I could do is measure positive pulse. And then I could measure negative pulse. Okay, and I think I can make this smaller. I say that. Can I make it? Yeah, there we go. There we go. Let's get just a couple of pulses, or actually, 1 pulse on the screen. Can I make that happen? Yes, I can. Okay, now, for this guy, I want to gate it for my zoom. Does that make any sense? If I do a single again. Nanoseconds, 400 nanoseconds. Yeah, okay, that makes sense. 0.4 microseconds is 400 nanoseconds, and 0.8 microseconds is 800 nanoseconds. So I got a 400 nanosecond while it's high, according to my data sheet. Oh my goodness, we can barely see the scope here. Here we go. We got it going. Here is the scope we're looking at, 400 nanoseconds and 800 nanoseconds. Here is a 400 nanosecond pulse. Here's an 800 nanosecond pulse. This corresponds to my data sheet. While the voltage is high, so right here the voltage is high, it says if it is a 400 nanosecond pulse that's a 0. So this is a 0. And then while it's low, a long pulse is 0. So this is 0, 0. So this is most likely just like 0, 0, 0, 0, 0, 0, 0, 0. I bet it's zeros all the way down. You can see if it's like, yeah, you can see it's short, long, short, long, short, long, short, long. That's 0, 0, 0. So that is turning the light off. If I did a single, oh, now look, I got some long, short, long, short, long, short. That's turning the light on. And that is some digital data going down, down the path, right? That's pretty cool. That's pretty cool, guys, I think. That was not a fail. That was a success. We made a blinking LED. It is still blinking in the background. We were able to decode it on the oscilloscope. We made everything happen. I think I'm going to declare success. I'm going to declare victory. Joe, sorry, I did have the scope window too little there. Did I get it big enough for everyone to see? That is the question. I am a rank amateur. I'm a rank amateur making this all work. But we were able to see. We were able to see. Okay. On the next episode, we are going to expand our lovely amplifier. We are going to, let's go back to just talking. We're going to expand our lovely amplifier by hopefully making the LEDs follow the rotary encoder. So I have learned a couple of things about my setup. The rotary encoder cannot control the volume of all the services directly. So it can't control the Spotify volume, it can't control the Bluetooth volume, it can't control the AirPlay volume, which is the point of the rotary encoder. So why would I have it? That has caused me to about face a little bit. So I purchased a digital potentiometer, and we are going to make the rotary encoder control my digital potentiometer, and we are just going to control the analog volume of the amplifier, which is awesome because that's really what you want your volume knob to do anyway. I just couldn't figure out how to make all that work and control the light ring. Now I can control the light ring, make it correspond to the volume level, and control the amplifier's volume, all using digital logic, which is something that I'm pretty comfortable with and only getting better at now that I'm starting to understand how the Raspberry Pi and Python interact together. Thank you so much for joining me. We did get a blinking LED. I don't know all the nerds in the world, but I would love to meet them. So please share this with a nerd in your life, and hopefully you can join me on Baby Friday when I'm going to do things a little bit earlier than even now. It's going to be 9 a.m. Eastern Standard Time. If you don't catch it live, don't worry, because it will be recorded and posted, and you can watch it at your leisure. Until then, have a wonderful week. If you have any suggestions, drop them in the comments below. I'd love to hear them. If you have a better suggestion for a single board computer, drop them in the comments below. I would love to hear it because this Raspberry Pi Zero is wonderful for many things, but I am beginning to doubt its efficacy as the brains of my Sonos-style amplifier due to the fact it throws off a lot of noise everywhere. And that is no bueno inside of an amplifier. I appreciate it. Had a great time, guys. Thanks for watching. I'll hang out in the chat. Talk to you later. Bye.